Hello everyone and welcome back to the channel. Today we're diving deep into a topic that's crucial for our future: smart water monitoring. These systems are the unsung heroes of our water infrastructure, but how much can we really trust the data they provide? Let's explore the challenges of sensor drift, the importance of calibration, and how new technologies are building a more reliable future for water management. So, what exactly is a smart water monitoring system? Imagine a network of tiny, intelligent sentinels deployed across our water supply, from the source all the way to your tap. These are sensors measuring things like pressure, flow rate, temperature, and water quality parameters such as pH, chlorine levels, and turbidity. They transmit this data in real time to a central hub, allowing water utility managers to see exactly what's happening instantly. This is a game changer compared to the old days of manual sampling, which was slow, expensive, and often missed problems until it was too late. With smart systems, we can detect leaks faster, predict demand more accurately, and ensure the water we drink is safe. It's all about making data-driven decisions to manage our most precious resource more efficiently. But here's the catch. These sensors, as brilliant as they are, aren't perfect. Over time, they can suffer from something called sensor drift. This is a gradual, often subtle deviation in the sensor's readings, even when the actual conditions haven't changed. Think of it like a bathroom scale that, over years of use, starts adding a few extra pounds to your weight. It's not broken, but its measurements are no longer accurate. In a water system, this drift can have serious consequences. A pH sensor that drifts might incorrectly signal that the water is perfectly balanced when it's actually becoming too acidic, which can corrode pipes. Or a pressure sensor might fail to report a gradual drop, masking a slow leak that's wasting thousands of gallons of water each day. What causes this drift? It's usually a combination of factors related to the harsh environments these sensors operate in. First, there's aging. The electronic components inside the sensor simply degrade over time, just like any other piece of technology. Second, there's environmental stress. Constant exposure to water, fluctuating temperatures, and chemical substances can take a toll. For example, a turbidity sensor, which measures water clarity, can get fouled by biofilm or mineral deposits that build up on its lens, causing it to report that the water is cloudier than it really is. Similarly, a chlorine sensor might lose its accuracy due to chemical reactions with other substances present in the water. Understanding these causes is the first step toward combating drift and maintaining the integrity of our data. This brings us to our most powerful weapon against sensor drift: calibration. Calibration is the process of checking a sensor's readings against a known, trusted standard and adjusting it to bring it back in line. It's like tuning a guitar. You play a note, compare it to a reference pitch from a tuner, and adjust the string until they match perfectly. For a water sensor, this might involve placing a pH probe into a standard buffer solution with a known pH value, say 7.0. If the sensor reads 7.2, you adjust it until it correctly reads 7.0. This process is absolutely critical. Without regular calibration, the data from our multi-million-dollar smart water system becomes unreliable and eventually worthless. Utility companies must follow strict calibration schedules, which can range from every few weeks to once a year, depending on the sensor type and the criticality of its measurement. Now, let's look at a real-world example to see why this matters so much. Consider a large urban water utility responsible for supplying water to millions of people. They use sensors to monitor residual chlorine levels throughout their distribution network. Chlorine is vital for disinfection, killing harmful bacteria and viruses. But there's a fine line to little chlorine, and you risk waterborne diseases. Too much, and you can create harmful disinfection byproducts and affect the water's taste and odor. Imagine one of their key chlorine sensors starts to drift, reading lower than the actual level. The automated system, trusting this faulty data, might inject more chlorine to compensate. This could lead to widespread customer complaints about the water's taste and smell. Worse, it could create potentially harmful chemical byproducts. Regular, meticulous calibration prevents this scenario, ensuring that the water remains both safe and pleasant to drink, maintaining public trust and safety. This is where the story gets even more interesting. We're now entering the age of artificial intelligence and machine learning in water management. Instead of just reacting to sensor drift after it happens, AI can help us predict it. How does this work? AI algorithms can analyze vast amounts of historical data from thousands of sensors. They learn the normal operating behavior of each sensor type under different conditions. The AI can then monitor the real-time data streams, looking for subtle patterns that signal the beginning of a drift. For instance, it might notice that a sensor's readings are becoming slightly more erratic or are slowly deviating from the readings of its neighboring sensors. By flagging these anomalies early, the AI can alert technicians that a specific sensor is likely to need calibration soon, even before its readings become dangerously inaccurate. This proactive approach is what we call predictive maintenance. It's a huge leap forward from traditional schedule-based maintenance. Instead of calibrating every sensor every 6 months, whether it needs it or not, utilities can focus their resources on the specific sensors that are showing signs of trouble. This is far more efficient. It saves time, reduces labor costs, and minimizes system downtime. More importantly, it enhances reliability by catching problems before they escalate. Imagine an AI system that not only predicts drift, but also suggests the most likely cause, whether it's biofouling or electronic aging, helping the technician prepare for the repair. This is the future of maintaining our smart water infrastructure smarter, more efficient, and more resilient. So, building trust in our smart water systems is a multi-layered effort. It starts with deploying high-quality sensors. It continues with a rigorous and consistent calibration program to combat the inevitable effects of sensor drift. And now it's being supercharged by AI-driven predictive maintenance, which allows us to be proactive instead of reactive. By combining robust hardware, diligent human oversight, and intelligent software, we can build a water monitoring ecosystem that we can truly depend on. This ensures that our water utilities can continue to provide safe, clean water to our communities, protecting public health and preserving our most vital resource for generations to come. It's a complex challenge, but with the right tools and strategies, it's one we are more than capable of meeting. Thank you so much for watching. I hope this gave you a clearer picture of the science behind keeping our water safe in the digital age. If you found this video helpful, please give it a thumbs up. And don't forget to subscribe for more deep dives into the technology that shapes our world. Let me know your thoughts in the comments below. See you in the next one.